This PowerPoint will focus on how to determine the relative strength of acids and bases. There are two periodic trends that we'll talk about in the beginning, and then we'll move on to some thermodynamics that help determine the strength also. The two periodic trends are that as we move left to right across a period, acid strength increases, and we'll learn why that is. And then as we move from top to bottom down a group, acid strength also increases. All right, so just quickly go over the definition of what a strong acid or strong base is. Strong acids and strong bases completely ionize or completely dissociate in solution. So, in other words, if we dumped HCl in solution, it would exist 100% as the individual ions, hydrogen ion and chloride ion in this case, and none of the original intact acid would be left. Same for a strong base. A weak acid or weak base, on the other hand, exists primarily in its intact, unionized form, and only a very small amount of the separate ions exist. And so here's a diagram which represents the same idea. A strong acid, again, exists as completely separate ions, and a weak acid, on the other hand, most of the particles are intact, undissociated acid, and there are only a few of the intact molecules that have dissociated. All right, so just a brief vocabulary. Electrolyte is any solution that conducts electricity, and what you need to conduct electricity are freely moving ions. How do you get freely moving ions in solution? Well, anything that dissociates to give you the individual ions would be a good electrolyte. And so a strong acid, that is one that dissociates completely into ions, would be a strong electrolyte. And a weak acid or base, which doesn't dissociate very much in individual ions, would be a weak electrolyte. So, in other words, the more freely moving, the more undissociated ions you have in the solution, the stronger it conducts electricity, the stronger the electrolyte is. All right, so now let's talk about the variables that determine whether or not an acid or base is classified as strong, and how you determine if one acid is stronger or weaker than another. Right. There are four factors we're going to go over. One thing that affects acid strength is the stability of the anion or the conjugate base that's formed. Okay, so if you look at this ionization reaction of some generic acid, HX, the more stable the anion is, or conjugate base, the more acidic the original acid is, okay? So it's kind of like you're more willing to go someplace if you know that place is going to be fun and safe, and you're less likely to go someplace if you know that perhaps it's going to be boring or unsafe. Same thing with this acid, okay? If what it results in making is stable, it's more likely to act as an acid. The strength of the bond between the hydrogen ion that's donated and the other atom that it's bonded to, the weaker that bond, the more likely it is to break, which is what needs to happen for an acid, right? It's got to give away a hydrogen ion. And so the weaker this bond, the more acidic it will be. A little bit more complicated are the last two bullets. We're going to talk about thermodynamic factors that affect the strength of an acid or base. Enthalpy and entropy, as always, those are the two variables that tie into free energy, whether or not something is actually going to happen. And so we'll talk about that toward the end of the PowerPoint. All right, so we're going to take each of those four factors individually. Let's talk about the stability of the conjugate base. Remember, the more stable it is, the more acidic the original acid. Why is that? Well, it has to do with electronegativity. So let's look at the four compounds down here and look at what they would form if they did act as an acid. In other words, what does an acid do? It donates a hydrogen ion. So what would CH4 form if it donated a hydrogen ion? Okay, it'd be left with CH3 with a minus charge. Ammonia, NH3, would be left with NH2 with a minus charge. Water, if it donated a hydrogen ion, would be left with the hydroxide, and HF would be left as F minus. Now I want you to look at all these conjugate bases. Remember, we're looking for the more stable. Which one of these four would be more stable and why? Well, the fluoride ion wins. All of these conjugate bases have to accommodate a negative charge, and some of them are going to do a better job. They're happier or more stable with a negative charge. And it turns out that fluoride ion is more stable because the fluorine atom is the most electronegative of these. Okay, and electronegativity means it attracts extra electrons. So fluorine wants, if you're electronegative, you want extra electrons. You're happy to have that negative charge. Oxygen's pretty electronegative, so the hydroxide's okay, stable. Nitrogen is less electronegative, so NH2 minus, yeah, I mean, it can form, but it's not real happy about it. Carbon, no way. It is not electronegative at all. It is very, very unstable with a negative charge. So CH4 is not acidic at all, okay? And of these four examples, HF, hydrogen fluoride, is the most acidic of these four, and it's because of electronegativity. So this is the first trend that says as you move left to right across a period, acidity increases. And so this is explaining why. It has to do with electronegativity. So as electronegativity increases, left to right, acidity increases. All right, so just kind of reiterating that, we're still on that first effect. Let's look at a mechanism for a compound acting as an acid. We know, hopefully, that hydrogen fluoride is polar. And so let's go ahead and draw the partial charges. Fluorine is more electronegative, so it gets the partial negative. Hydrogen gets the partial positive. And we also know that HF can hydrogen bond, can have the intermolecular forces of hydrogen bonding. And so when we put hydrogen fluoride in water, there exist hydrogen bonding intermolecular attractions, which we know are strong, between water and the hydrogen fluoride molecules. And because of that, you can kind of think of this oxygen on water as pulling on the hydrogen ion. Because of that, that pull on the hydrogen ion weakens the HF bond, okay? And it makes it easier to remove that H plus to let HF act as an acid. Okay, so weakening that bond between the hydrogen ion or whatever it's bonded to helps the substance become more acidic. So the fact that hydrogen fluoride is quite acidic has a lot to do with the fact that fluoride is an electronegative atom. because not only does that mean that the conjugate base, F minus, is stable, it also means that that hydrogen fluoride itself is very polar. There's quite a bit of separation of charge because of the electronegativity difference between fluorine and hydrogen. And because of that more condensed partial positive charge in hydrogen, it's more strongly attracted to the electronegative oxygen and water. So this is the type of question you should be able to easily answer now. If you're asked to compare different acids and they all exist in the same period on the periodic table, right? You are looking for the acid that is farthest to the right for being more acidic. Okay, so we know at this point that hydrogen fluoride is more acidic than the others. All right, let's talk about another periodic trend, and that's the acidity going from top to bottom down a group. It's a little counterintuitive. It has nothing to do with electronegativity, and you'll actually get it wrong if you get mixed up and consider electronegativity. All right, so let's look at all of the hydrogen halides: hydrogen fluoride, chloride, bromide, and iodide. So really what we're doing is we're going down the family of halogens. It turns out that hydrogen iodide is most acidic of these four. And of these four, hydrogen fluoride is least acidic. I know that's got to be counterintuitive to you because you're like, wait a minute, fluorine's the most electronegative atom. Why isn't that making it more acidic than hydrogen iodide? Because there is a second factor that is actually more important than electronegativity, and that is bond strength. Okay? That is more important than electronegativity. And it turns out as you go farther down on the periodic table, the atoms get larger and larger, right? So if I were to draw, let's draw fluorine up here. I thought I turned that off. Sorry for that dinging. And let's see, then chlorine's a little bit larger, bromine's a little bit larger, and iodine is huge, okay? It turns out that the larger an atom is, the weaker it bonds with other substances. Kind of makes sense, right? Because if you have a really large atom, it can't get very close to any other atom to make a really strong attracting bond. And so fluorine makes very, very strong bonds. So even though fluorine's very electronegative, that bond strength with the hydrogen ion is so strong that it doesn't want to let go. And so we haven't talked much about pKa. It's kind of like pH, but the bottom line is that HI is the most acidic and HF is least acidic, okay? So as you go down, and this would be true on any group, any vertical group on the periodic table. As you go from top to bottom down any group, it is going to get less and less acidic. So this slide just summarizes what I said a little bit more clearly, probably, than I did on the last slide. All right, so this would be a typical question that you should be able to answer now. And again, if you're comparing acids, different substances, and ask what's the most acidic, check out where they are in the periodic table. It's the first thing you should do. And in this case, oxygen is toward the top. Underneath oxygen is sulfur. Underneath sulfur is selenium. And finally, tellurium, okay? And so tellurium is the most acidic. It's at the bottom. And that's because tellurium itself is much larger than, let's say, oxygen. Okay, and because of that largeness, the bonds that it makes with hydrogen are much weaker, okay, and easier to break. So these hydrogen ions are more acidic than the ones on water. All right, I just have kind of a food for thought question for you. Since we're talking about comparing relative acid and base strengths, most acid-base reactions are reversible. That's what these double-headed arrows mean. So let's go in the forward direction. Hopefully you remember that nitrogen-containing compounds are basic. That means that water in this reaction is acting as an acid. And so hydroxide would be the conjugate base, and the ammonium ion would be the conjugate acid. So in the reverse reaction, if we were to go in this direction, and NH4 plus and OH minus were our reactants, then NH4 would be the acid, right? Hydroxide would be the base. So which direction is favored? I mean, are there going to be, at the end of the reaction, are there going to be more products or more of the original reactants? And what determines that? It turns out that you use the same type of rationale we've used so far, and you ask yourself which pair of acids and bases, the reactants or the products, are more stable. And hopefully you know by now that nature prefers stability, lower energy. And so the side that has the more stable acid and base is going to be the side that favored. If you were asked to determine which of these sides, the reactants or the products, were the more stable acid and base, which one would you choose? Well, I'll just let you know now that the neutral water and neutral ammonia are more stable than hydroxide and ammonium. That's not always the case, but in a lot of cases, most molecules would rather be neutral than charged, and that is the case here. Okay, we know that if we just have water by itself, it's not going to just go off and react. Pure water won't. Now we're going to talk about thermodynamic factors that can affect how strong an acid or base is. They're a little bit more complex than the periodic trend, so you may need to concentrate a bit more on it. We're going to talk about both enthalpy and entropy considerations, because if you remember from thermodynamics, we have to consider enthalpy and entropy in order to predict spontaneity, or delta G, free energy. Just kind of an overriding principle I want to emphasize is if we have an acid that is considered strong, that means that it's very reactive, and it also means that it's unstable. It is strongly reactive because it's unstable in the form it's in. Okay, so if an acid is strong, it will make a lot of product. The products will be favored, we say, and the products will be more stable than the reactants, which means less reactive. Okay, so you could also say the opposite. If you had an acid that was weak, what does that mean? That means it's relatively unreactive, and it also means that it is quite stable. Things that are stable do not want to change. They don't want to react, okay? And then you could say the opposite for the products, okay? The products would be more strongly reactive and less stable. So let's look at the thermodynamics of some acid-base reactions. I said we're going to talk about enthalpy and entropy. So just some of the generics. When we talk about enthalpy, that's heat energy changes, we have to consider the strength of the bond between the hydrogen ion and the atom it's attached to. And we talked about that already, right? The weaker the bond, the more acidic. We also will consider stability of the conjugate base, which we've already talked about too. So these are the two key factors that are going to affect the enthalpy change of an acid acting as an acid. The entropy change, that's how usable the energy is. When, hopefully you remember that when an acid dissociates into the ions, the entropy increases, right? Think of freedom of motion, remember, when you talk about entropy. So freedom of motion is definitely higher for these individual ions than it is for this original intact acid. However, there's another consideration. Since these acid-base reactions that we're talking about are occurring in water, this acid has to dissolve in water first. And when it does, it separates into the ions. But then what happens to those ions? They become solvated by water molecules. Remember that solvation means the solvent surrounds what it's dissolving. And so it turns out, what do you think solvation does to entropy or freedom of motion? Hopefully you can see that that's a negative for entropy, okay? Salvation shell is kind of like putting the ions in jail, okay? They just got free, and then the solvent molecules are surrounding them and kind of trapping them. So that's a decrease in entropy. So what's the net effect? If entropy increases with ionization, but then decreases again with salvation, what's the overall net effect for a change in entropy of an acid dissolved in water? Well, depends on what the individual ions are. So let's go a little bit more in detail about enthalpy and then entropy. We're going to talk about enthalpy first. And we've got to think about all of the interactions that occur between the acid and water and the ions in water to decide what the net effect of delta H is. Is overall, is energy going to be released or is energy going to be consumed? So just to kind of reiterate what I said a couple of slides ago, when you break any bond, it is an endothermic process. It requires input of energy. That is unfavorable, right? But how unfavorable is it going to be? Well, it depends on the strength of the bond that's being broken, right? We've talked about that, right? So the weaker this bond strength is, the more acidic it's going to be. Now, we've only broken one bond, and that's HX. Now, what about bonds that we make? The only bond we make is an oxygen-hydrogen bond when we make the hydronium ion. So it goes from water, then we add a third hydrogen ion, and we've made hydronium ion. So we've made one new bond, and making any bond is an exothermic process. It is favorable in nature. It releases energy. It turns out that if we're looking at this generic acid-base reaction or ionization of an acid in water, regardless of what the acid is, every acid's going to make hydronium and make a new OH bond, right? So we can almost ignore the contribution of making that bond because every single acid's going to do it. So what's going to determine the key difference in enthalpy for an acid and water is the strength of this bond. There's one more factor that's going to play into enthalpy, and that is the salvation energy, the energy involved in surrounding the conjugate base with water molecules. And that will be different, right? Because each conjugate base is going to be different depending on the original acid you started with. So just to summarize, because that was a lot of words on the last slide, The energy absorbed upon breaking the hydrogen ion bond will depend on the strength of that bond. So that is unique to the acid. The energy released when we form an OH bond in the hydronium ion is the same, regardless of the acid. So we're going to kind of ignore that. And then finally, salvation, the energy released, okay, that's an exothermic process, okay, when salvating the conjugate base also depends on the nature of the original acid. So we really have to look at the first and third bullets to understand the enthalpy change. Here are actual values, okay? This is for the bond strength only. As we already knew, right, it's easier to break the hydrogen iodide bond than it is to break the hydrogen fluoride bond. And that's because of the size of the iodide, right? So that's not a surprise. The bonds get weaker. So bonds weaker in HI, which means HI is more acidic, okay? HI is most acidic. All right, that's the bond strength enthalpy. Now we also have to consider the enthalpy change involved in salvating the conjugate base, which we haven't talked about yet. So just to kind of reiterate salvation, because we've talked about that quite a bit in the solutions unit too, it's important to understand. Anytime you dissolve something in water, and we'll just use fluoride ion as an example, that substance that dissolves gets salvated or surrounded by the water molecules, whatever the solvent is, it's water in our case, and that releases energy. Notice that the delta H is negative for salvation, which is favorable, right? Negative delta H is favorable, and it better be favorable, otherwise it wouldn't want to dissolve, right? So salvation is a stabilizing factor. It's a good thing. It stabilizes particularly ions in solution. So it is exothermic, it's energetically favorable. But it's how energetically favorable it is depends on the ion itself. So let's compare the enthalpy of salvation for all of the halide ions. Interesting. Look at these delta H, heat of salvation values, or enthalpy of salvation, same thing. So it turns out which one of them is most strongly salvated? Which one of them releases the most energy when it becomes salvated by water? It turns out that fluoride is most strongly salvated, okay? That means that the most energy is released when the fluoride ion is salvated. So the more negative delta H is, the more favorable it is. So the salvation of fluoride ion is most favorable, most exothermic. So does salvation make something more acidic or less acidic? That's a good thing, okay? If salvation is favorable, that means that HF wants to, again, be acidic because the water is going to take care of the conjugate base. It's going to stabilize it. So salvation is making HF a stronger acid. So pause for a minute because that's the opposite direction. Okay, we just got done talking about how bond strength makes iodine the strongest acid, right? HI, the strongest acid, because of its weak bond. But now, wait a minute, going in the opposite direction is salvation. Iodine, I mean, it's still exothermic when it's salvated, but only about half as much as the salvation for the fluoride. So what's the net effect? We have two factors we have to consider in the change in enthalpy, delta H. One is bond strength and one is salvation. So let's look at the net effect of both of these. Okay, so overall, the delta H for this generic reaction, looking at all the halides, is the following. Now, I don't know if you remember that the delta H for bond energy, let me write what those are down so we can compare them. Alrighty, so here are the enthalpy of breaking the bonds, and you can see that the bond energy for hydrogen iodide is a lot lower than all the rest of them. Notice also that all of these delta H are positive. So breaking a bond is always unfavorable, okay? But it's less unfavorable at this point for hydrogen iodide. So I've just written the enthalpy change for salvation over here. Now, all of the enthalpy change for salvation are negative. They're all favorable, but HF is the most favorable. So over here, breaking a bond, HF was the least favorable, and over on salvation, it's the most. So what's the net effect? Because they kind of seem opposing forces. What's the net effect? Well, the net effect is shown right here. The total delta H for the entire ionization process of each of these acids. It turns out that the net effect, they are all favorable. Okay, the delta H, the enthalpy is favorable for all of these acids. But whereas we thought HI might be most favorable because of its weak bond strength, it turns out that HBr is the one that's actually most favorable from an enthalpy standpoint. And most interesting, I think, look at HF. If we only looked at enthalpy, we'd say, oh, well, HF why isn't it a strong acid? That negative sign, doesn't that tell us it's going to be spontaneous? No, 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 no. Remember, to determine spontaneity, we have to look at enthalpy and entropy. So we're not done with the story. So let's talk at the entropy change for all of these four. So here we go. It's actually temperature times entropy change, but you can still see the trend. Remember that we want, if delta S is positive, it's favorable. Okay, so we want entropy to increase. So the only favorable one with respect to entropy is HI. Entropy is working against all the other ones. Now, how is that possible? Because, let's see, we've always learned, right, that the entropy involved in ionizing or separating something intact acid into its individual ions, that the entropy is positive, that's favorable, right? What's going on? How do you get these negative values? Well, it turns out that is salvation, okay? Due to salvation, remember I showed you that, for example, let's salvate an anion, that it's kind of like the water molecules are putting the ion in jail. They're reducing the freedom of motion, therefore reducing the entropy. And it turns out that that effect for hydrogen is really pronounced. Okay, so delta S for hydrogen fluoride, is very unfavorable, and that's got to be contributing to the overall acidity of hydrogen fluoride. So the net effect, we've talked about enthalpy and how all of them, the enthalpy for all of them is favorable, okay? Just barely for HF, but it's still favorable, it's still negative. Then we just now talked about the entropy change and how the only one that's favorable as far as entropy goes is hydrogen iodide. Let's look at the net effect for free energy with delta H and delta S both incorporated. Now it makes sense, right? Turns out that hydrogen fluoride is the only hydrogen halide that has a positive delta G, which means it is the only one that is non-spontaneous as an acid. What does that mean? If delta G is positive for an acid, that means it's a weak acid. We don't consider it to ionize or act as an acid spontaneously, at least with water. Okay, all these numbers are for the acid and water. But it turns out that the rest of the hydrogen halides have a delta G that's negative, so they all spontaneously act as an acid in water, and all three of them are considered, because of that, strong acids. So delta G, the bottom line is, if delta G is negative, it is a strong acid. If it's not negative, if it's positive, it's a weak acid. So the bottom line is the acid strength, the overall acid strength still goes in this order, which we said at the very beginning of this PowerPoint, but it's not just related to size. That's kind of an easy way to explain it, but it's an incomplete way. It turns out that HI is the strongest of these four acids for both enthalpy reasons, because the bond is weaker, and also for entropy reasons, because iodine is not solvated very much. Okay, and not solvated much is a good thing, because that means that entropy is not lowered much. Remember, solvation lowers entropy. It restricts freedom of motion. But because iodine is so large, it doesn't get solvated as tightly, and so there's not as much of a loss of entropy. Now, the last several slides talking about thermodynamics can get really confusing, and that's an area that you're going to have to explain. So you may need to listen to that or read the textbook, go through it a couple of times to really understand it. All right, just a couple of slides left, and these aren't quite as deep. What if I asked you to look at these three acids, okay? And the hydrogens, well, pretend they're an acid. And the hydrogens are all bonded to an oxygen. So we can't talk about electronegativity or periodic trends. Let's draw a Lewis structure of them each for a minute and see if that helps. Okay, so we have water on top, then this is actually methanol, and then this third one, C, is acetic acid. See if you had to come up with some type of guess, what might it be and which one is more acidic, okay? So look at what we want to do is look at the area or the atom that's going to be donating the hydrogen ion. Now they're all different, but which one is most acidic? It turns out this can be explained with resonance structures. Now, you probably learned briefly about that in 1211, but the bottom line is when you have double bonds or you have p orbitals, and that's back when we were talking about like electron configurations where you'd have something like 1s2, 2s2, 2p3, etc. So when you have valence electrons in p orbitals, they can participate in double or triple bonds. And it turns out that if you have lone pairs of electrons, they also sometimes can exist in a p orbital. And when you have these p orbitals all lined up with each other, it turns out they can share the valence electrons, the electrons that are in these p orbitals. And by doing so, they delocalize the negative charge, which stabilizes it, okay? So I'm just going to write that out. So delocalization, anything that delocalizes or spreads out the negative charge helps stabilize that molecule. So delocalization of negative charge stabilizes the conjugate base. And remember, anything that stabilizes the conjugate base makes the original acid more acidic. So you just have to remember that every time you have a double or triple bond does this too, that you have p orbitals and you have potential delocalization of a negative charge. And this is how it's often shown, the delocalization. It's just shown the dotted lines represent the electrons in the p orbitals or pi bond that are now, instead of being localized between two atoms, are now spread out and delocalized among 1, 2, 3 atoms. So if you see resonant structure, that's going to stabilize the conjugate base and make the original acid stronger. So here's a couple of examples for you to try out. It turns out that sulfuric acid and nitric acid, if you've got to remember what acids are strong or not, so memorize the 6 or 7 strong acids and bases. But both of these are strong acid, okay, which means they completely dissociate into ions. All right, and nitric acid is another strong one. And remember what strong means, okay? These are strong, which means they're reactive, which means the product is more stable, right? The stronger the original acid, the more stable or more stable and stabilized the conjugate bases are. So let's figure out, why are these conjugate bases stable? Turns out they both have resonance. So let's see if you can draw a Lewis dot structure for HSO4 and nitrate. See if you can identify where the resonance is. So if you think you can do that, go ahead and turn off the video for a minute and try to do it yourself. So I'm going to go ahead and draw the Lewis dot structures out. The first thing you always do is count valence electrons. Nitrogen has 5. Each oxygen has 6 valence electrons. There are 3 oxygen. And then there's an extra electron. That's what the negative charge means. So I have 24 valence electrons I have to place in my Lewis structure. So the first atom in a formula is almost always your central atom, almost always. The first step in Lewis structures is to draw single bonds with all the other atoms. And you can see now that we have used 2, 4, 6 electrons. We have to use 24. The second step is to give the outer atoms an octet. All right, so how many electrons have I used now? I have used all 24 electrons. But if you go back, and I encourage you, if you haven't done so already, go back and learn the more complicated rules for drawing Lewis structures. And again, I do have a lecture on that. If you just Google my name, if you haven't found my YouTube channel, Lori Maffei YouTube, and then just search for Lewis dot structures. But it turns out that once you've used all the valence electrons, if the central atom does not have an octet, and we can see the nitrogen doesn't, it only has 2, 4, 6 electrons around it, that you have to start making double and or triple bonds to give that central atom an octet. So if we take one of the lone pairs of electrons and move it to make a double bond, let's look at what our structure is. All right. So this is the final Lewis dot structure for the nitrate ion, NO3 minus. So I'm going to go ahead and put brackets in the minus sign. But it turns out this structure has resonance. So it turns out that this oxygen, where we've shown the double bond, is really identical to the other two oxygen, and that double bond can equally be placed on any of those oxygen. So the resonance structures would look like this. Or I could put it on the one oxygen I haven't shown it on yet. So all of these resonance structures are equivalent. Okay, there are 3 of them. And it's just moving that double bond around, the 2 electrons in the pi orbitals, or the pi bond, that are delocalized through all 3 of these oxygen. And so because of that, NO3 minus is an extremely stable conjugate base, and that is why HNO3 is a strong acid, because of the great stability of the nitrate ion due to its resonance structures. Now let's look at sulfate ion. Alrighty, so I'm going to go ahead and take both hydrogen ions off of the sulfuric acid so that all we're looking at is the sulfate ion. So let's go ahead and draw the Lewis dot structure for it. Sulfur has 6 electrons. There are 4 oxygen, each of which has 6 electrons, and there's a -2 charge, and that means 2 more electrons. So the total number of valence electrons we are working with here are 32. And so let's put sulfur in the middle and draw single bonds to begin with to the 4 oxygen. Then we're going to give each oxygen, each outer atom, an octet, and then count how many valence electrons we've used. There we go. So it turns out, if you count them, we've used all 32 valence electrons. And sulfur has an octet. So are we done? Well, again, this is one of the more complex Lewis dot structures, one of the kind of obscure rules, but it's important. And in atoms that can expand their octet, which means they can hold more than 8 electrons, and you may remember from 1211, those are atoms on row 3 on the periodic table or below. So that'd be rows 3, 4, 5, 6, and 7 can all expand their octet or hold more than 8 electrons. And the rule is, if by expanding the octet you minimize formal charge, you must do so. So right about now, you're probably rolling your eyes thinking, formal charge, oh my gosh, I have to remember everything from 1211. Well, it turns out you actually do. Sorry about that. But I'm going to review it quickly for you. So the formula for formal charge, and again, you may want to review it if that sounds like a foreign language to you, is you take the number of valence electrons that an atom has normally on its own, right, before it is involved in any compound making, and you subtract from that the number of valence that atom has in the compound. Okay? So the number of valence electrons that atom has normally minus the number of valence that atom has in this compound. All right, so what am I talking about? You've got to find formal charge for every single atom in a compound. So the formal charge for this oxygen normally has 6 valence, okay? That's what I'm doing here when it's on its own as an atom. So then ask yourself, how many valence electrons does the oxygen have in this compound? Well, let's see, it has 2, 4, 6. Now, there are 2 electrons in every single bond, but since it's a bond, it's a covalent bond that's shared, the oxygen only gets 1 of them. And so the number of valence electrons the oxygen has in this compound is 7. Okay, 2, 4, 6, and then 1 of these. So the formal charge on that oxygen is -1. All these oxygens are equal. So each one of these oxygens has a formal charge of -1. That's not good. I don't know if you remember, but we want to minimize formal charge in a compound. Let's see what the formal charge is on sulfur. Well, sulfur is in the same group as oxygen, so on its own as an atom has 6 valence electrons. How many valence electrons does it have in this compound? Well, it doesn't have any lone pairs. It only has 4 single bonds. And it only gets 1 electron from each of the shared covalent bonds. So in this compound, sulfur only has 4 valence electrons. So sulfur has a formal charge of +2. All right, so that's not good. Every single atom has a formal charge. And so we're going to go ahead and do that last step for Lewis dot structures that says if you can minimize formal charge by expanding the octet, you must do so. So here we go. I'm going to show you how we do that. So we started out with this Lewis dot structure. And I haven't forgotten that it has a charge of -2. So we would have to show this just to be accurate. All right, and I'm going to minimize formal charge by introducing a double bond. So I'm going to take one of the lone pairs on one of the oxygens and use them to make a double bond. And then I'm going to count formal charges again. Well, we already know what the formal charge on these single bonded oxygens are, right? They're still -1. Let's see what we've done to the formal charge of this oxygen with a double bond and sulfur. Well, this particular oxygen, of course, as an atom on its own is 6. Now let's count how many it has now. 2, 4, and it gets 1 from each of these bonds, 6. So now the formal charge on this oxygen with a double bond is 0. That's good. We've minimized formal charge. What is it on this sulfur? Well, sulfur starts with 6 when it's a sulfur atom on its own. How many does it have in this structure? Well, it gets 1 from each bond, right? 1, 2, 3, 4, 5. All right, so the formal charge on sulfur is now +1 instead of +2. So we have minimized formal charge. Can we do it one more time and minimize formal charge further? So in other words, can I go ahead and take another lone pair off one of these other oxygen and make another double bond? Let's see. If we have reduced formal charge again, then that's a good thing to do. So now we have 2 sulfur oxygen double bonds. And we know now that the single bonded oxygens have a formal charge of -1, that the double bonded oxygens have a formal charge of 0. So what is sulfur? What formal charge does it have? Well, it gets 1 electron from each bond. 1, 2, 3, 4, 5, 6. So the formal charge on sulfur now is 6 - 6, or 0. All right, so once the central atom has a formal charge of 0, stop. Okay, it's not going to get any better than that. So this is the final acceptable, stable, best Lewis dot structure for the sulfate ion. And of course, it has resonance structures. So these double bonds that we've shown on these particular 2 oxygens can be moved around wherever we want them to. So I could redraw an equivalent resonance structure that looked like this. And I could move these double bonds around in any grouping that I want to on this sulfate. So again, this has resonance that makes it very stable. And therefore, that explains why H2SO4 is also a strong acid. We only have 2 more slides. So we've been talking about from the perspective of acid. What about a base? Which of these pairs, let's look at these 2 first, is the stronger base, okay? So stronger base means more reactive, and it also means less stable. Okay, so of these two, does your intuition tell you which one the stronger base is? In other words, which one would be more reactive, which one would be less stable? I'm hoping that you would pick hydroxide. Hydroxide is clearly stronger, more reactive than water. We know water doesn't really want to react with anything unless it does, but in general by itself. How about comparing these two, ammonia and water? Well, notice off to the right here that if you can't really tell, sometimes if you have, not all the time, but if you have one substance that has a charge and the other one doesn't, the one with the charge is usually stronger because nature it would prefer to be neutral. But if they're both neutral like this, and you have to determine which one's stronger, now your intuition might be telling you correctly, because I've drilled it in, that nitrogen-containing compounds are typically bases. And then we know that water is neutral. So NH3 is the stronger base. Let's take a look at this last set. So which is the strongest base of these? There are a couple ways I can think of attacking this. Again, remember that strong means reactive, and it also means unstable. So can you look at these and determine which one is less stable? Which one is least happy with the negative charge that it has? And what I'm hoping you remember is electronegativity, right? They all have a negative charge, and the more electronegative, the easier it can accommodate that negative charge. So carbon's the least electronegative. No way, it doesn't want that charge. So therefore, when it has a negative charge, it is unstable, which makes it reactive, which makes it a strong base. So CH3 minus is the strongest base of these. And fluoride, because fluorine's so electronegative, is quite happy with that negative charge. What does that mean? That means it's stable. If it's stable, it's unreactive, which means it's a weak base. So make sure you have those associations correct. Stable, unreactive, weak, and strong, reactive, and unstable. So what we're going to get into a bit next, and I alluded to that several slides ago, is now that you kind of have a feel for identifying the relative strength of comparing acids and bases, we're going to look at overall acid-base reactions. And as I said before, most of them are reversible. They can go both directions. So the question we're going to want to answer is, which of these arrows is favored? In other words, will the products be more stable? Okay, in other words, less reactive. Boy, my handwriting's going downhill, right? More stable means less reactive. It also means weaker acid and base. And, or would it be the reactant side? In this case, this arrow is telling us that the products are favored. So we know the products are more stable. The more stable side is going to be favored. So that means the reactant side is less stable. We could also say that because it's less stable, it's more reactive. And we could also say because of that, that these are stronger acid and base than the other side, which is pure water, right? So we're going to do a bunch more of those. Which direction does the equilibrium lie? That means towards the right, which would be towards the products. Are the products favored? And that's saying the products are more stable if they're favored. Or if the equilibrium lies to the left, that would mean the reactants are more stable and favored. And nothing's really in the middle. That's just made up. That is it, finally. Sorry for the length of this.